My name is Rustam Stolkin. I'm Chair of Robotics at University of Birmingham. I'm also Royal Society Industry Fellow for Robotics, part embedded with the National Nuclear Lab Limited, UK. I'm Director of the National Centre for Nuclear Robotics, and I'm also the Chair of the Expert Group on Robotic and Remote Systems for the OECD's Global Nuclear Energy Agency. The National Centre for Nuclear Robotics was founded in 2017 with a £14 million grant from the Industrial Strategy Challenge Fund, originally a consortium of 8 universities. Via our Flexible Partnership Fund, we expanded to include 12 research institutions across the country from Scotland down to the south coast. In the first 3 years, we produced well over 300 peer-reviewed papers. In addition to robotics and AI and associated engineering, we also expanded to the humanities, political and social sciences, and issues of management, regulation and policy. We've delivered a very large number of world-first landmark deployments of robots on nuclear industry sites in the UK and internationally. We've also had impact across a number of other industrial sectors, and we've undertaken significant international leadership in EU robotics and also with the OECD's Global Nuclear Energy Agency. I can't discuss in detail all of our research, but it spans a very broad range from advanced robotic manipulation and air and ground vehicles, robotic vision and perception, and also the human aspect and cognitive factors of human-robot interaction, advanced machine learning and AI, sensor systems, radiation-resilient electronics, and autonomous mapping and navigation. The past 3 years has seen the creation of a number of very significant robotics installations at both Birmingham and our partner sites. These are major robotics infrastructure for long-term use by the research and industrial communities. In this case, you can see the very large 3-ton robotic manipulators set up at our Birmingham Tyseley site, which are the same robots as are going into the Sellafield plants for robotic waste sorting and segregation. So National Centre for Nuclear Robotics spans a very broad range of different kinds of robotic activity, but we are particularly strong on advanced manipulation with robot arms and hands. This is work from University of Birmingham on fully autonomous robotic grasping, and these are objects for which the robot has no prior knowledge and no prior models and doesn't require even any training data. And what we're addressing here is the very difficult problem of grasping and removing objects from very cluttered random heaps of objects. National Centre for Nuclear Robotics has a major strength in advanced robotic manipulation. This is currently world-leading work on fully autonomous grasping and manipulation of unknown objects of arbitrary shapes from random heaps using computer vision. This is some very complex work from Lincoln, which grew out of the previous work in H2020 Romans project as well, further exploring the concept of heaps, so disentangling objects from heaps. And also what you're seeing in these still images is the idea of a robot poking a heap of objects so that a vision system can disambiguate each object from the other objects. So a vision system doesn't really know where one object ends and another object starts when you're looking at a heap, but by disturbing the heap with the robot arm, these objects can be further disambiguated and perceived. So another way that we can augment computer vision is with tactile sensing. And here on the right, you can see a robot feeling its way around a hexagonal bolt, using its torque sensors to perceive shape. And on the bottom right, you can see that it's successfully reconstructed the hexagonal shape of the bolt head. On the left, you're seeing a very advanced dexterous hand with tactile sensor arrays, and it's making successive tactile glances of an object to gradually improve its understanding of the object's shape. But at the same time, it's also simultaneously refining its grasp pose to find the most robust and secure grasp while it's also exploring. Adding additional kinds of sensors can further assist with this problem. And this is work from University of Bristol using XRF sensors to look at objects in a heap and tell the different materials of the objects from each other, which can help for sorting and segregation and also disambiguating objects. So what we previously showed you was fully autonomous manipulation, but here is work from University of Lincoln working with University of West England at Bristol Robotics Lab on teleoperation. So using one robot as a master to control an identical remote robot in a leader-follower paradigm. And you can see that using both robots as leader and follower provides a very intuitive and easy to use control interface. So to support this remote handling and control of remote manipulators, we need situational awareness, and this is work from Bristol Robotics Lab, University of West England on telepresence and advanced ways of allowing operators to perceive what's happening at the site of the remote robot in the hazardous zone. So this is work from Queen Mary, and this is design of very novel kinds of manipulators, soft manipulators, and this is called an eversion manipulator, so it extrudes itself from the inside, and you can see that this can travel through narrow pipes and tubes and openings, and it can deliver cameras and sensors to hard to reach places. It's soft so that it will not damage any delicate pipework or other infrastructure. And there's also been interesting work developing novel forms of sensors, novel tactile sensors and things like that. And Queen Mary has also been working on teleoperation of manipulators with haptic feedback and soft manipulators as gripping tools. So at the opposite end of this spectrum from the lightweight soft manipulators is work happening at Lancaster University on very, very heavy duty, powerful hydraulic manipulators. And I believe they're the only lab in the UK, possibly in Europe, that actually does work on these heavy duty hydraulic machinery. And this machinery is widely in use throughout the nuclear industry, so it's particularly important. It has extremely complex dynamics and control problems to control the actuated joints in the ways that you want. And related mathematics can be used to look at the complex control problems also of quadcopter drone robots. So Lancaster's work there was on the low-level control of the joints of the manipulators. At Birmingham, we focused more on the high-level planning of the motions. And here you can see a mobile manipulator planning cutting actions and cutting paths. And what is difficult here is that you have to plan the motion of the wheels of the vehicle, the motion of the joints of the arm, and the motion of the cutting tool over the cut surface. And all three of those motions have to be planned mutually with respect to each other to be mutually consistent. One of the remits from the Industrial Strategy Challenge was that, as well as having a strength in nuclear, we should also show how these generic robot technologies can be applied to other industries and other societal problems. Here we're looking at handling of non-nuclear waste, and in particular in this case, how to deal with the very large lithium ion battery packs in electric vehicles, which is actually a potentially very hazardous form of waste. And here you can see robots performing very, very complex disassembly operations, cutting and unbolting and removing components from these very, very complex waste streams. So bringing us back to the radioactive environment, all of these robots need to operate in various kinds of radiation fields and radiation environments. University of Essex has done fantastic work building partnerships with NASA Jet Propulsion Lab and Rutherford Appleton Lab and the National Physical Laboratory. And these organizations have radiation facilities that they've made available to Essex. And what you can see here is Essex putting cameras and sensors and circuit boards and computer chips inside radioactive chambers and bombarding them with radiation to see how they deteriorate and model that deterioration. And on the bottom right, what you're seeing is a camera in a radiation field, and those bright speckling is the radiation particles hitting the pixels of the camera. And to overcome these challenges, Essex has been developing very novel methods to make systems on chip resilient, and that includes self-healing electronics. So electronic systems that detect their own faults and computers detecting their own faults and self-healing to rearrange themselves to repair those faulty parts. Some of this is now working using deep learning to learn how to automatically adapt firmware and software and hardware to overcome these faults. There's further work also now that we can put complex electronics into high radiation environments. University of Bristol has carried out deployment with Sellafield there with a crane mounted sensor package, the suitcase if you like, and this is building up 3D maps of the stored material in radioactive waste stores and mapping the radiation emissions from them as well. So just to reiterate, we've been doing this for real. So top right is the first ever deployment in history of a autonomous AI-controlled robot arm in a radioactive environment. This is work that University of Birmingham did with National Nuclear Lab at the Preston Springfields nuclear plant, laser cutting contaminated steel. And this is using AI autonomous grasping as an operator assistance technology to aid a human during teleoperation. And on bottom left, you can see this being deployed at National Nuclear Lab's Workington site in Cumbria, controlling very heavy duty industrial manipulators. And this is a nuclear industry worker testing the system out. And this is being deployed under full nuclear safety regulation and national security regulation. NCNR has always been very prominent in educational outreach. We have over 10 years collaboration with the Royal Institution, and I myself have a longer collaboration with USA using hands-on practical projects with robots, building robots and building sensor systems in the classroom as ways of teaching science. And through the Royal Institution, we've done summer schools every year, but we also help them to reach out to masterclasses to schools nationwide. That's been very difficult during COVID, but we've been assisting the Royal Institution in developing masterclasses in a box. They send a box out to school districts and keep that work going. So